Last time there were some people who trickled in after 9:05, but that's okay. I'm going to start anyway. Because I'm going to start now because we got a lot to cover today. So, okay. Starting again from where we keep starting at every lecture. We're starting at this point of light weighting and structural optimization is about geometry and materials. All right? You have to make materials that have high strength to density ratios or high stiffness to density ratios. That's how you get light, stiff, strong structures, fatigue-resistant structures too. In the first lecture, or the second lecture actually, we covered materials, how to actually design materials to give you those ratios that you want. This is very different than the mechanical engineer's tradition of looking in tables and using those values. This is inventing materials with the values that you want rather than what's available to you. In the last lecture, we talked about geometry. We took a car body and we broke it down into beam elements. We looked at the loading on each of those beam elements and then identified which materials would be most efficient to put in each of those elements to get the maximum stiffness or the least weight or the maximum fatigue resistance or crash resistance or whatever we decided to design for. Today we're going to continue discussing geometry rather than materials. And I want to warn you that today's lecture is going to seem somewhat disconnected, maybe not of any real interest in what we're really doing. It is abstract, but I guarantee you that the information is very valuable when it comes to light weighting or designing any structure. So just bear with me here. The math is going to get a little sort of abstract, okay? But just we'll go slow, understand it, and then next lecture you might see a little bit clearer where this comes in handy. Okay, fair enough? I want to go back to this problem right here. Because I don't think I did a very good job of explaining it last time. So if you remember, we discussed this at the end of last lecture, but I want to go through it again. So just to recap, you have a column, okay? You have a column that's under a compressive load, okay? The column is a hollow tube. It has diameter D, and it has wall thickness T, and it could fail by buckling, a local mode or a global mode, okay? But it could fail. We don't want it to fail, but we want to have the lightest design we can. There are two design variables here. They are the diameter of the tube and the wall thickness of the tube. Okay? If you look closely at my sketch there, you'll see that it's constrained at the top from rotating at the top. So the top of this beam can't sort of rotate. So you really are in pure compression. Okay? You can begin to think of this in terms of a design space. This is a concept I really want you to think about, design space. On one axis you have the wall thickness. On the other axis you have the diameter of the tube. With those two variables, knowing the density of the material and the length of this column here, it's very easy to start plotting constant weight contours. And I've done that, and they're labeled W here, okay? Some weight contours, right? This is uphill, that's downhill. So the further you go up this way, you're getting heavier. And the way you go down, and when you go down this way, that's not a W, is it? You're getting lighter, okay? W1 is greater than W2. Okay? So this is really straightforward. You guys could, I'm sure you guys, all everyone in this room could punch this out in Excel in 5 minutes. This is easy stuff, okay? Understood? Okay. Now, the objective here is to minimize W, like we said before. We're going to call that an objective function. Minimize weight, minimize W. That's what this class is about. You're subject to the constraints of diameter. The diameter can't get bigger than 4 inches, and the tube thickness can't get less than 20,000ths of an inch. And the diameter to stiffness, diameter to T ratio has to be greater than 10. Those are called side constraints. They're geometrical constraints. We're imposing these. Maybe it's based on what we can buy from the McMaster car catalog or some shop, whatever it is. You're stuck there. You have to stick in those limits. The next constraint is called a behavioral constraint. Okay, and as I mentioned before, we're trying to avoid buckling here. Local buckling or global buckling. Now we've defined some constraints, G1 and G2, which are the stress in that column minus the critical stress for for buckling, whether that's local or global, right? And we've got two constraints here, G1 and G2. And they are equal to the difference between those two stress levels. If that difference goes to 0, that means we failed. We hit the point where it fails. Understand? So therefore, the region of interest is where those constraints are greater than 0. Okay? And we're going to take those constraints, they're G1 and G2. Okay, see those there? It's purple and red. You guys see that? And I'm going to do my best to do a horrible job of sketching it on this diagram right here. Too bad we don't have colored chalk. We don't have colored chalk? No colored chalk. Okay. All right. These are W. Okay, I'm going to put a G function in here. This is going to be my G1, which is a function of X and or T and D. Okay, that's G1. Now I'm going to put another one in here, which I know from doing this beforehand kind of looks like this. And this is another function, G2, which is also a function of T and D. Okay, so this is kind of hard to see because these are the same colors. But I thought maybe by actually watching me physically draw it on the board, it might be a little bit clearer than just looking at the colors on the board. Okay, so weight, okay, and then G1, and then G2. Okay, and then we also have this constraint about D. D has to be less than 4. So that happens. I'm just going to draw that, make up some line. This is my D less than 4, less than or equal to 4. Okay, so this is the diameter. That's the maximum diameter we're allowed to pick. Then this for one buckling constraint, G1, and then the other buckling, G2, then the other buckling constraint, G1 right here. Okay, sorry, right. Here. I didn't draw this very well. G is right here. Okay, sorry. Okay, this is kind of a mess, I'm sorry. G1, G2, and then this D constraint. Weight is going down as you go this way. So that puts us at this vertice right here. That's going to be the point of lowest weight. So this combination of D and T is what can give you the lowest weight because it satisfies these constraints. You have to be this side of the G1 line, okay, and you got to be this side of the G2 line, and you want to go the minimum on these W contours. That puts you here. That's the lowest weight solution right there. And by the way, there's one other constraint I didn't draw on here. There's a T equal to 0.02 inches, so 20,000ths of an inch right here. Okay, so remember we talked last week about that idea of having these tubes that are under bending and you could get the same stiffness at a lower weight by going bigger in diameter and thinner wall. Remember we showed the two bicycle frames, we showed the green frame and the white frame, and the weight was, the white frame was lighter than the green frame even though it was stiffer. This is what we're dealing with here. You're dealing with a big D and a small t. This vertice right here, that's your point where you get the minimum weight solution, subject to these constraints, D and G1 and G2. Okay, does everyone understand this? Because this is the foundation for everything else we're going to talk about. This concept of exploring a multi-dimensional design space to find an optimum solution. Okay, everyone understand? Paige.
That just happens to fall very close to your D and T constraints, right?
Right.
It's just a function of the problem.
It just came out that way. Yeah, but it makes physical sense, right? Based on what I was saying last time about bigger diameter, smaller wall thickness, it just happens to work out that way. Okay, does anyone else have any questions about this? This is, I think, really the crux of what we're looking at. And I'm going to show you one more example before we get more abstract.
Does that point take into account any kind of factor of safety for buckling too? Like
No.
Very low minimum, do you have to add a little bit?
In the real world, yes. In the real world, yes. But it's a good point. The way you would factor that into this problem is you would put that in your G1 and G2 constraint. That would become part of that equation. You might have that minus some factor of safety, okay, or times some margin that gives you the factor of safety. But but the point you bring up is a good one, is that you can use the same methodology to take into account a factor of safety. The factor of safety can become your constraint. Okay? Everyone get that? His question was, how do you, does this have a factor of safety in it? Whenever whenever I've been involved with designing any kind of mechanical component, you do your finite element calculation, and you say, okay, this is how stressed out it is, and then you say, okay, let's put a fudge factor in there of 1.25 or whatever it is just to make up for something we didn't know, so we don't actually get a failure in the field and somebody gets hurt, and then we have to get Steve involved, right? So lawsuits.
Actually, I was thinking, I mean, what I think about when I see this is bicycle tubes.
Exactly. Me too.
That's what that equation is. I don't know how.
Right.
So that would be the way you would account for variability in material. Professor Eber always talks about the material only being as strong as its weakest
defect. Yeah. Right.
So that would be the way you account for variability in material that you buy from a manufacturer.
Exactly. You get, when you buy material, when you buy a tube, when you buy a Columbus tube from Columbus in Italy, you'll get a spec sheet with it. You'll get a cert, and they're claiming that they did mass spec or X-ray diffraction or something, and they figured out the composition, and this is what it is, and we tested the material, and these are the strengths we got. And most of the time they're right. Most of the time the values are what they claim or higher. Every now and then you get a batch of material that isn't. You know, they tested over here on the coil, but the part of the coil over here had some defects, and this was actually weaker. So that's why you put in a factor of safety, to make up for those unknowns. And I would hope that in a mechanical design course that some of you would have had, I guess, because some of you are MEs, you would have discussed this. Okay. Does this make sense, guys? Any more questions on that? Okay. We're going to move to a slightly more complicated problem. Oh, there we go. That goes up. Okay, this goes down. If you can't read anything here, let me know. My writing's not so good. That's why I do everything on PowerPoint. Okay, this is the famous 3-bar truss problem. Although the paper that I learned about this problem was published in the 80s, this problem was actually solved in the 50s. It was a NASA problem, actually. And it goes like this. You have three rods. These are rods. These aren't hollow. You got 3 rods, okay, and they attach at a point at the bottom. And they're oriented at about 45 degrees to one another and 45 degrees to the horizon. And the cross-section of these rods are A1, A2, and A3. That's some cross-section. Don't worry right now about whether that's diameter or width times thickness. That's just called diameter, your cross-section A. It doesn't matter. Again, the problem is you want to minimize weight of this structure here. And you have 2 loading cases, P1 and P2. They're not necessarily loaded at the same time. They might be loaded at different times. For the purpose of this discussion now, we're just going to focus on P1, the first loading condition. This is an example of how you might simplify a problem. One of the constraints on this problem is that the design has to be symmetric. So because of that, we're going to say that A1 equals A3. So the cross-section of A1 and A3 are the same. The stress in those two are the same. So we started with 3 variables, and now we're down to 2 variables. This is a method. That sounds pretty trivial, right? But this method of simplifying the problem by making assumptions about things that are equal or symmetric. Before they had finite element analysis and big powerful computers that could solve complicated finite element problems, the people at NASA used to solve problems like this all the time. And they had computers that were enormous. You guys probably heard about this. There's some funny pictures online, computers the size of a room. But it's a simplification method. That's all I want you to really know. The weight is given by W, which is a function of A1 and A2, okay? And it's given by that equation right there. Just notice that N is the length between the nodes, so that you can see N is up there. So I wish I had a pointer. N is up there, okay? And then rho is density. You can just think whatever you want it could be. It could be steel, it could be 7.8, whatever it is. It's just some density, okay? So that's the objective function. The objective function is to minimize weight, which is equal to that equation. The constraints are that the stress in those rods can't exceed 20,000 psi in tension or 15,000 psi in compression. That's the strength constraint, okay? It's pretty weak. Most materials have more strength capability than that. And this is, by the way, this is another, what's your name again? Tim, this is another place where you could use your factor of safety right here in this constraint. Maybe this material is a 30 KSI material, but you're only going to say 20 is only what we're going to let it have. We'll let it see. Then we're going to define more constraints, which really are a function of the first constraint, H1, H2, H3. And these are the maximum allowable stress minus the actual stress in that member, the stress I comma j, where I is the loading case. I'm sorry, I is the member, and j is the loading case. So I is that is the member, A1, A2, E3, one of those bars, and then j is the loading case, P1 or P2. And we've purposely designed these constraints, H1, H2, and H3, so that if those constraints are held, if we meet those constraints, we won't go beyond the stress level that we have said is the maximum stress we're going to allow in these rods. Okay? So let's think about this. Let's plot this out. Okay? We're going to have the same two-dimensional design space. We got what do we got? We got A2 on the A1 on the bottom, and we got A2 on the vertical. Okay, right? So A2, A1. These are the cross-sectional areas of those structural members. And then very easily with that equation, we can plot out constant weight contours. And they're just, in this case, straight lines rather than curves. Okay, again, listen closely. Uphill, higher weight is this way, and lower weight is that way. Did I do that wrong? That's right, okay. Downhill. Weight is this way. Weight decreases that way. Weight increases that way. Then just as we did before, we can start plotting out those values of the constraints H1 through H3 on this same graph. Okay. By the way, the stresses can be calculated very quickly, easily using those equations there. Okay, I've already solved that for you. I'm going to go ahead. I'm going to start plotting some of these out. So I'm going to take first. I'm going to take H. Oh boy, I think H1 is like this, and then H2 is like that, and then H3. God, I can't see this. Okay, that's H2. Okay, then there's this one here. Okay, so this one is, guys, correct me if I screw this up. This is H what?
H3.
That's H3. This one's H2, and then wait a second. This one's H1, and then this one's H2, right? Okay. And based on the way I've written the constraints, we've designed these constraints, these functions, H1 through H3. We want to be this side of H3, this side of H1, and then this side of H2. Right? So that means the feasible region is this area here. This is the feasible region. These are the areas where we could design these things. We could pick an A1, an A2, and an A3, and that would not violate our constraints. We would not be in a situation where we're above the stress limit of those rods. Okay, and looking at these constraints, I didn't draw this real well, but I'm going to go over here and try to explain it because I didn't draw that real well, because this is a key point. So here is H1, H2, and H3. Downhill, right? Weight is decreasing this direction. So we want to find somewhere that doesn't violate these constraints, that's furthest down towards this corner, the lowest weight combination, right? And that is very clearly at this point right here, right? Because the way that this H2 or H1 constraint is set up, this is the point where it dips down furthest into W. But this is a really interesting point. It's kind of intuitive to say, like, I'm going to design some structure. I want it to be as light as possible. It makes sense that I use all the mechanical capability of all the structural members I have in order to support the load. And if I maximize the stress in every element, it's going to be the lightest solution, right? And that's the intuitive thought. And for years and years, I thought that was the case until I learned about this. It's not always the case. Sometimes you can actually achieve a lighter solution by not having all the members stressed to the max, right? So here's 2. This is the point where all the members would be stressed to the max. Here's point 1, and it's actually a lower solution. See, if I drew another weight contour through here, that would actually be heavier than here. You see that? So this is known as the simultaneous failure point. or the fully stressed design. And it's actually heavier than the absolute minimum, which is there. Completely unintuitive solution. Can I see that? You see that what's interesting about that? That we thought that, this fully stressed design should always be the lightest weight. It turns out it isn't. It isn't always the lightest design. And that was, I think, one of the big accomplishments of this exercise, was getting to that point to understand that this is more complicated than just, okay, let's stress everything to the max and hope for the best. Okay, do you guys see what we did here? We did the same thing here as that we did in the previous exercise. Okay, you have a two-dimensional design space, A1 and A2. You can then very readily draw out constant contours of weight. Then you think, what is the direction? What is the direction that's uphill, weight's increasing, and what is the direction downhill where weight is decreasing? Uphill, downhill. Does that sound like any kind of mathematical function you guys have seen before in calculus? Maybe in a later on calculus course? Kim, you know something, right? No?
No, I forgot all of that.
You forgot all this, okay. So the term I'm going to talk about in a minute is called a gradient. Okay, you guys remember this term gradient? Gradients are wonderful things. Being able to calculate a gradient is a wonderful thing. It's an amazing thing, what it does, and you'll see why in a second. It's something I never appreciated when I took calculus until I started getting into this stuff. But what we're really looking at here, when we talk about going uphill and going downhill, we're saying, what's the gradient? Is the gradient increasing or is the gradient decreasing? Okay? Okay, so this guy here, Lucian Schmidt, he died about 2 years ago. He was a professor at UCLA. I could have met him because I took summer school when he was at UCLA one year when he was a professor there. Fortunately, I wasn't smart enough. I didn't know about this field. I wish I'd gone and talked to him. He's really the pioneer, the fundamental, the first guy in this structural optimization. He coined the term structural synthesis to describe when you want to put load between some boundary conditions. What's the most efficient way to do it? How do you synthesize this structure to give you the lightest possible solution? And these 3-bar trusses and the one before it, he's pretty much the guy who did those in the 50s. And I've got some books at home. There's a whole other things he did. Some of his grad students went on to be pretty famous too. I'll discuss one of them later. But this is really guy number one. I don't remember where he went to school, but he was a professor here at this place, at this institution, for about 5 years, and then he got lured away to Case, and the military probably loved this guy because he probably saw lots and lots of interesting problems that helped him save fuel in fighter jets and other planes and whatnot. But the reason I bring this guy up again is that if you're interested in reading more about this, there are some wonderful papers that he wrote that are very understandable that you can go look up in your library and read more of Lucian Schmidt's papers. Okay? Okay, so I want to lay out sort of a mathematical general framework for what we just did with our design, with our minimum weight design here, okay, with how we went and did this. So I'm going to lay this out very abstract. Suppose you had a mountain, and this should seem familiar to you guys. Suppose you had a mountain. Suppose you are a skier and you want to find the top of the mountain so that you can ski down and have the most fun and get to the highest speed on the way down. But you don't actually know where you're going because you're blindfolded. Someone drops you off at the bottom of the hill and you have to find a way to the top, but you're blindfolded. Okay? So, gesundheit, squared. So as this blind guy, you start walking up this mountain, okay? And you have your feet to know where your feet are feeling heavy and when they're feeling light, but you're making your way up this mountain. Okay? And you're walking up the mountain, you feel like, okay, I'm gaining an altitude, I'm gaining an altitude. Then you run into a fence. Okay, that fence is the same analogy as a constraint. Like I gave you these H1, H2 values over here. So you hit your constraint, you hit that fence, and you go, okay, I can't go any further, I'm stuck here. So I'm just going to pivot some direction, and I'm going to start heading again. And I don't really know where I'm going. So I start heading up, okay, this feels like the right direction, I'm headed uphill. Boom, you hit the other fence. You hit the fence G1. And you zigzag back and forth until you finally find the top, so you don't feel like you're going any further. You get to the top and you say, I'm not getting any higher, my feet feel lighter somehow, I'm not getting any heighter. Maybe if you really went high, you're like running out of oxygen. So the formal way of discussing this is that you have an objective function, f, which is a function of the two design variables, d1 and d2. and you want to maximize f. Your objective function is f. You want to maximize your objective function in this case. In this one, we did minimize. In this one, we're doing maximize. Got it? You're subject to constraints, G and H. There could be many constraints. I've only drawn 2 fences here, but there could be many, many fences. So this is just a basic description of what I just said. Okay, you're walking up this mountain, you're hitting constraints, and this is the idea of optimization. You have some sensors in your body, whatever they are, maybe oxygen deprivation, that tells you when you're going up and when you're not. Again, you can do this exact same concept for minimizing things. You know, you can go down, you can invert this. Your objective function, your objective could be to minimize your objective function rather than maximize it. And again, you're subject to constraints G and H. Okay, I want to play a game here. Let's see if it'll let me do it. Come on. There we go. Okay. Okay, we're going to play a game here. We have a function here, f of x. All right? And I've plotted out this function with the vector x. X has 2 variables in it, x1 and x2. So this, again, is a 2-dimensional design space. And what we're going to do as a team here is we're going to pick, so if underneath these blue boxes are numbers, okay, numbers of that function. So we've got this grid that goes from negative 0.1 to negative 1 for x1 and then negative 0.8 to 0.8 for x2. Okay, and we're going to go through this and we're going to delete these blue boxes and we're going to try to find the minimum of this function f of x. Okay, before we start, I want you guys to open up, wake up for a second, take a deep breath, and I want you to watch very carefully what happens as we do this as a team. We figure out where it is. Okay, watch very carefully how people's logic evolves to try to find the minimum of this function. Okay, so where is the first box you guys want to delete? Somebody pick a box.
Center box.
Okay, the center box. So would that be, okay, I can point with this, can't I? Would that be here?
Yep.
That one?
Yeah.
Okay, what do you guys think? You like that box? Okay, I'm going to delete that box. Okay, the value there of the function f of x is, what does that say, 8.9? Okay. So we don't know if that's a maximum or a minimum. We have no idea. So what are we going to do next? Pick a different box. So which box do you guys want to pick? Next to it somewhere?
Yeah, to the right.
To the right. Okay, that's see, that's your right. Okay, so my left. Wait a second. I'm still looking at the screen. Okay, it's confusing here for me with the right and left. I always like global coordinate systems like north, east, south, and west. Okay, so you guys want to go to my right. So you want to go here? That one? Okay, I'm going to delete that one. Okay, the number is 8.6. Did we get higher? Did we get increase or decrease? Decrease. Decrease. We decreased, okay? The value went down. Our objective function f of x went down. So now let's pick a next box. Do you go a different direction? Do you keep going in that direction? What do you do?
I would pick around 8.9, but
You want to go here? I'm going to go beneath, below. That's fine? You want to go here? Okay, I'm going to go here, all right? Delete that one. So we got 7.8. So we went lower still. Okay? We chose that middle point. We got some value. We picked a direction at random. And then we said, okay, great. Then we picked another direction at random. And it turns out it was the second random direction was better. So which of these 2 directions would you guys want to go from here to try to find where this function gets lower? Would you want to go again to the right or down? You want to go diagonally? So you want to go here? This way? That way? That one? Okay. We got 7.4, so we went lower again. You want to go right? It's a bigger decrease, yeah. Okay, so you want to go over here?
I want to go all the way to the right and all the way bottom.
Here? There?
Yeah.
Okay. That you got 9.52, so you went up.
Wow.
It's okay, we're learning. We're learning. This is good. So we can go back and use the logic of what we've seen before and where we've seen gradients, right? We've seen a gradient here. We've seen a change in value. We've seen a gradient. So where next? 7.4? Okay, down to the left. So you want to go here? Right there? Okay. 7.2. So we're better. Paige got an idea here.
Yeah, I want to go down into the right from
7.6.
Whatever.
7.8, this one right here?
Yeah.
You want to go here?
Yes.
Okay, let's delete that one. 6.6. So that went downhill. That was an even steeper gradient.
Let's do it again.
Okay, you want to go down that way again?
Yeah.
But watch very carefully what we've said here. We've said we found a steep gradient here, a steep downward gradient. So let's just keep going that direction and see what we find. So you want to go right here. Right there?
Yep.
Okay. 5.77, so you're even lower. You want to keep going that direction or we want to go somewhere else? You do want to keep going that direction. Okay, so we're going to go here. Okay, 5.22. We're still going down. You want to keep in that direction?
Yeah.
Okay, just notice that we're going one step at a time. Before we went this big, huge direction. So we took a big step in a direction. It didn't work, it turns out. But now we're going little shorter steps, but we're finding a more reliable pattern. Okay? So we're going to go here next. 4.85. So we're down again. Now, if I remember correctly, I think that is very close to the minimum. So the minimum was actually one step the minimum was actually one step here to my left. Okay, but that's actually the minimum right there. Okay, so think about what just happened. I'll repeat it again. Okay, we picked some point at random, right? Victor picked some point at random. He said, just try the center. We got a number. We didn't know what that meant. We didn't know if that was high or low. So we picked a random search direction and a random step. In this case, the step was basically one unit, one box, and we found a lower number. Okay, and then we tried a different search direction. That didn't work. And we tried another search direction. We weren't sure if it worked. So finally, we said, okay, let's go back to that first direction. And we kept taking short steps until we finally found the minimum. Okay, but this should give you some flavor for what it means to be blindfolded walking up a mountain, right? Not knowing where the top of the mountain is or going down a cave and finding where the minimum, the bottom of the cave is, right? Okay? This is optimization. We have a two-dimensional design space here, x2 and x1. And we found the minimum through using, I wouldn't say a total random walk, right? I mean, we actually used a little bit of intuition about were the numbers, was the objective function, the f, was that going up or down, okay? And we found the solution. It's interesting to look at this and say that we had some constraints. We were within a very small box, actually. That box is located right, put this back up on the board. There we go. This box was actually, just a small subset of the area of the design space we could have looked at. We looked at, it's like negative 0.1 to negative 1 on one side, and then some similar kind of distance on the horizontal, but that was only one small subset of a bigger design space. Here's the bigger design space right here. And this has its own minimum as well, which is at that point 1, 1, which is actually 4. The objective function there is 4. But we're still looking inside a box. This is still a constrained problem. We've found a local minimum. Okay, scientists, mathematicians talk about global minimums or global maximums, and these things theoretically exist, right? These functions, as you guys learned in your math classes, go on infinitely. They go on to the edge of campus, to the end of Boston, across the Atlantic to Portugal, whatever. I mean, design spaces are infinite, unless you put constraints on them, which is what we're doing here. We're putting constraints on these. Okay, let me kind of put a little bit finer point there. So, suppose you had a single-dimensional design space. Call it x. X is your only design variables. And you know that the objective function is this funny curve right here. And the funny curve has a couple places on it that could be a minimum, a local minimum, or a minimum within those constraints. The problem on the right, on this side, that is called an unconstrained problem. I'm showing a subset of possible x values, and this could go on forever, but I think you know from your calculus classes that it's very easy to find the minimum within this region we're looking at here, right? You can You guys did this a million times as freshman engineering students, right? You took calculus and you took the first derivative, you figured out where it equals 0, and then you found those points where it equals 0. And then at that point, at those, in this case, there's 3 places. There's 3 places where you get a 0, right? You took the second derivative, and the second derivative, it was, if you figured this thing was concave up, then it was a minimum. If it was concave down, it was a maximum. So at point A, we have a minimum within this domain, and at point C, we have a maximum, and at point B, we have an intermediate. The first derivative there is equal to 0 as well, but it's not it's just a very local minimum. And if your constraints were closer to right around B there, then that would be your point of reference. Now, what we've looked at, if these design examples, and pretty much all the design examples you're going to experience in life are going to be constrained problems, because we can't build structures that extend from here to Portugal. Unless it's a cable, I guess, right? Maybe that's anyway. So we look in terms of constraints, and when you have constraints, like you see on my left here, okay, when you have these constraints, you can't do something really easy like take the first derivative, set it equal to 0, and then take the second derivative, figure if it was concave up or concave down. This becomes a lot more complicated, but this is reality. This is what's practical. And the design problems you're going to experience in real life, you're going to be in the constrained problem area. And the mathematics community, going back hundreds of years, has worked on all kinds of ways of solving this. The most common method is called the gradient method, and that's the one I'm going to mostly talk about today. More recently, maybe within the past 20 or 30 years, they've come up with some interesting novel ways of attacking this problem too. They have interesting method names like genetic algorithms or genetic search methods, and then there's particle swarm, which is about bees. I don't know if we're going to get that today, but maybe we'll talk about it next time. Okay, so you guys see the difference between a constrained and an unconstrained problem. Your local minimum, God, I wish I had a pointer. Your local minimum for this side is right there, but the first derivative there isn't equal to 0. It's hardly equal to 0, right? It's got some positive value. See the difference, guys? It's really important here. That with an unconstrained problem, you can just use derivatives. When it's multidimensional, more than just one dimension, they have this thing called a Hessian. It sounds like some type of German soldier from World War I, but they call it a Hessian, and it's some kind of matrix of first derivatives and second derivatives that allows you to figure out a maximum minimum in a multidimensional constrained problem. I'm not going to get into that because you really need computers to start solving stuff like that. What we're going to do here is we're going to mathematically formalize what we did last time, what we did in that example, the game we played with the blue boxes, right? Suppose you have some design space made up of design variables x1 and x2, right? And you want to, there's an objective function, call it f. The idea is to minimize this objective function. Okay, and again, minimizing f, downhill is this way, uphill is that way, right? Now I've put this really weird symbol here. It looks like an upside down triangle. Okay, that is the mathematical symbol. I think they call it a del. Anyone can correct me if I'm wrong. It's called a del. That's a term for gradient. When you have a gazillion variables and you understand what f is for those gazillion variables, you can calculate out a gradient. You might have to use computer algorithm or some kind of finite element analysis code, whatever it is, but you can calculate out a gradient of f. That gradient of f will always point to the maximum of the function. I find this kind of fascinating. Like, you have this random design, space with this function, and there's this function. There's this gradient thing that'll point towards the maximum. So in the gradient search method, you calculate out. Okay, you look at the design space. You come up with an equation for the objective function, and then you pick a random point, just like we did, just like Victor did. He picked the center of that design space before. You pick a random point, okay, of f, and you start there, and then you start searching from there. At the point, we'll call it x0 here. That's the first point we've chosen. That's the point that Victor chose. At x0, you can calculate a gradient there for f, and it's shown right here. This is the gradient of f at x of 0. Okay, and you know it points some direction. In this case, it's pointing, to the upper left, in my left. Right? And it makes sense. What the way search algorithms work is to take the negative of that gradient as your first search direction. Say it again. You take the negative of that search direction, of that gradient. That becomes your first search direction. Okay? And that's very close to what we ended up doing if you think about it. Right? We picked a diagonal, and we kept going down that diagonal. And then you choose a step length, alpha. So you've got gradient s, which is a vector that points the direction that's opposite of the gradient for f, the objective function. Okay, remember, we're minimizing f here, not maximizing. We're minimizing f. And we're going to pick a direction, or a search step, alpha. The first alpha, so we pick this design vector, x, with values of 2 and 1. Okay, that's right here. Okay? This s, this is the opposite of this is the negative of the gradient at that point x0. And our design step is going to be 0 for the first one. We're going to calculate out f of x, or f of alpha, which is 10. Okay? So that's like the number we got at the center of that graph. And now we're going to apply that vector direction, and we're going to pick a step length, alpha. Okay? And I've copied this to the next page, so that thing that's in the box there, that's exactly the same you saw on the other page. I just copied it here so you don't have to memorize it. It's very easy to start plugging in these numbers then into this equation right here. This one right here. Okay, so go ahead and plug in your search direction, plug in your alpha, your step, and you get this guy right here. Okay, and you come up with an x value, and then you can go ahead and you can calculate out an f for that. So if your first step is 1, you're headed in that s vector direction, then the value becomes 8.4. So you went from an f value, a deductive function f of 10 to 8.4. So you went down. So that's a good direction. But it's not surprising because you went opposite the direction of the gradient. And then you plug in a 1.5 for your alpha. Your vector direction s stays the same, but you take a bigger step. Just like we did before. Next page, what's your name? Solder, right, solder. Just like you picked before. You picked a much bigger step. You picked a bigger alpha. You went all the way to the corner. We're going to pick a bigger alpha. We're going to pick a 1.5. We're going to end up right here. But there's a problem with this. There's a constraint g, the function g. The constraint is that g has to be greater than 0. Less than 0. G has to be less than 0. At this particular value of alpha, that step, that 1.5, we're actually getting to a positive g. So we've violated the constraint. The constraint is right here, this g1, okay? We're over here now. So we went too far. Our step was too big. We violated the constraint. You can't do that. So we pick an intermediate. We pick an alpha of 1.25. And we end up right here at g equal to 0. And this is the minimum right here, right there. Okay? So this is an iterative process. You have an objective function. Okay? You start at some point. Could be any point. You calculate at the gradient at that point. That gradient tells you what's the direction of the maximum. Which direction is f going up? Okay? You pick the opposite of that as a search direction, just like we did before. And then you pick some step length. And then you keep trying different steps iteratively until you find the lowest value of the function. Okay? So this is really just doing the math behind what we did sort of intuitively in that experiment before.
Once you reach a point, do you just go all around that defined step size? Just make sure that's the local minimum?
That is one way you can do it. The way that this happens in the real world, and I'll show you this if I have time here, but I might not. The way this happens in real search algorithms is you start at multiple points. You pick multiple points in this design space, and then this algorithm will start doing this search direction, gradient calculation, search direction, step length. We'll start doing that for multiple points at once, and eventually they all begin to converge on one area. That's called the problem converging. So that answers your question, I'm sure. But that's the point, is that you can't do this starting in one point. You have to really start with multiple points and then find a position that it converges at, that all of them go to a certain value, a certain place in the design space. Okay, back to more math. So if you focus Here's basically the same thing we just looked at. Okay, you've got f of x, which is your objective function. You've got g of x, which is your constraint. You've got design space x1 and x2, and here is a curve right here for f of x. At some point right here, you can calculate out a gradient. The gradient points this direction, normal to the tangent of that curve. Okay, and then you can begin to break this up into areas that you consider to be usable, feasible, and unusable. And this is helpful. The algorithms will do this to help decide which direction to go, what their S direction is. And this is a particular case where you can't just pick a search direction that's the negative of the gradient because you run into this constraint. The constraint is right here in gray, this g of x. Okay, but the angle between the g curve, okay, 180 degrees around the g curve is the feasible region. The angle between your f of x and your g of x is usable, feasible sector, and then is a usable and feasible, and then the direction normal to the constraint g of x is unusable, right? Because it breaks the constraint. See that? It seems trivial, but you're going to see why this is important in a second. This allows you to define search directions. This allows an algorithm to pick search directions. It uses these matrix dot products, which I don't remember how to do. I used to be able to do them, but this is important. Understanding that there's a non-usable region, there's a usable region, and then there's a feasible region, then there's a usable and feasible direction. And they're defined by this equation here, which is just really a dot product of the vectors S and F. Okay? The minimum of function f inside the constraints is actually right here. At that point, the gradient of the constraint and the gradient of the function f are opposite each other. When that occurs, or let me say it a different way, in order for there to be a minimum, this has to be true. You have to have these gradients canceling each other out. Okay? The directions cancel each other out. Mathematically, you might have to put a scalar in there. So Paige is thinking about this. You might have to put a scalar in there, which is called a Lagrange multiplier. You're not changing the direction, but you're multiplying it times a scalar so that the two cancel each other out. So lambda here is a scalar. Lambda is called the Lagrangian multiplier. Do you guys remember studying those in calc? Lagrangian multipliers? I think that was certainly not a first quarter calculus class. But anyway, you can begin to sort of imagine this in your head. As you move right or left of this minimum here, the gradient of f and g won't cancel each other out. Right? These two are going to start as you go down this curve. Since the gradient is always normal to the curve at that tangent point. As you move right or left from that point, these guys are going to start going, wacky with respect to one another, and they're not going to cancel each other out. When they're not canceling each other out, that's when you cannot have a minimum or a maximum. And this is formalized, what's called the Kuhn-Tucker condition, okay, which is basically says exactly what I just told you, that the gradient of the function, okay, minus the constraints cancel each other out is a requirement to get a local minimum or local maximum. So depending on whether it's a minimum or a maximum, you might add those to the initial vector. The objective function. In this case, it's w. All right. So this is a necessary condition in order to find a minimum or maximum. Okay, guys, you don't have to understand this real clearly. Okay. Right? Because whatever computer algorithm you're going to use is going to do this for you. Right? Nobody probably does this by hand anymore. But the point I just want you to understand that this is what you really got to understand. What you really got to understand is that there is a mathematical way to define these maximum and minimum. And the computer algorithms that you'll be using, or you may use someday to do structural optimization or some other optimization, it's using this concept that these gradients have to cancel each other out. That's a necessary condition for it to be a maximum or a minimum. Okay, do you understand at least the high level of this? Don't worry about the Lagrangian multipliers. It's really confusing for right now. If you want to go back and read about this, you can read all day long about Lagrangian multipliers. I still have a couple questions, but But you get the idea here, that it's a cancellation of these gradients that tells you for sure you're at a local minimum or local maximum. Okay? Does everyone have at least that understanding of this? Okay? Paige?
Got it.
Okay. Okay. So here's a diagram. I think this is the last. We got till 10 o'clock. Is that right? We're over now? 9:55. Do you guys want to stop or you want to go through this guy real quick? This basically just does what I just showed you. This is an algorithm for the search method, for the gradient search method. And you pick some point at random, you calculate out the gradient of the objective function at that point, you pick a search direction that's the negative of that gradient, and then you go in that direction, that's your vector, times some step length. And you decide whether the function's going up or down, the objective function is going up or down. Okay, that gets you to another point. At that second point, say right here, you calculate out the gradient at that point, and then you pick a search direction that's the opposite of that search direction, or the opposite of that gradient at that point. Then you go some other step, okay, and you check to see if the objective function is going up or down. If it's going down, then you stop there and you calculate another gradient, and then you pick a search direction that's the opposite of that gradient. Then you go a little bit further. You do this iteratively until it looks like the function isn't going down anymore. And again, like I mentioned, in reality, the way that these things work, these algorithms work, is they pick many, many points throughout the design space. And they do this exact same thing, and they check to see if they all find the same minimum. And if they do, then the computer reports it back to you as a minimum. Okay, today was a little weird. I admit that, a little bit too mathematical. But understanding at least the concept at a higher level is what you're going to need to understand in order to really design, to really understand how optimization of light weighting works. Could be something else. It could be cost. It could be stiffness. It could be compliancy. Whatever it might be. But this is the basic idea of what it is, of how this works. Next time we'll talk real quickly about genetic search algorithms and particle swarm search methods and the plus and minuses. And anyway, that's we'll get there next time. Any questions, anyone? Welcome to stay. I'm here for a while if anyone wants to talk about this. All right.